new class. So sorry. All right, so just FYI, I still don't have email yet. I know other faculty do, but there's something very odd going on with my accounts. I don't know, maybe they tried to hack my accounts directly or something. But I cannot really access my email yet. But I don't know if that's such a major issue for y'all because I don't get a lot of email anyway. So, but I did update the materials on Blackboard. And I'll also update it more so people can, I know you probably, with spring break, maybe some folks are inclined on getting a little bit ahead, so I'll make sure that that's there. The homework that was due this week, I pushed out till next week. So the exam that was supposed to be Tuesday, we'll have the Tuesday coming back from spring break. I'm assuming everything will be regularized by then. But we kind of do need to keep moving forward. So I've also assigned the homework on chapter 6, bending, and I'm going to kind of stagger those things moving out a little bit to get back up to where we should be. I think it's only about a class and a half behind. And, but it'll be kind of compressed over the next couple of weeks. So it should be like immediately, you know what I mean? So, were there any questions on the logistical issues? I also put a new course plan because it's been a little while since I updated that, and that has the new exam on it. Okay. So I also bumped out the stuff in mastering engineering. So we're good. We got a question? Did you push back the reports? What reports? We know what reports do. We still have the first project. I'm going to sign the second project, okay? And I'll have the reports. I'm almost done with grading the reports. Kind of took a little longer than I expected. There's no report due today per se, okay? For this week, okay? At least I don't think so. If there is, and I don't know about it, then I guess that basically means, right? All right, so today I wanted to get started on, well, if there are any chapters, I'm sorry, if there are any questions on chapter, questions on chapter 5, I'm going to start with chapter 6, okay? So we'll do a couple of PowerPoint slides here, I think, to get started. So chapter 6 is on bending. So we've talked about axial problems, right? Then last chapter we talked about torsion. And now we're going to go to our third and really our kind of final major mode of mechanics materials, right? So again, this is all based on idealized deformations that give us the stresses. And now this one is bending, right? So bending is, they're all very important, but bending is probably the most important one. It happens very often. And unfortunately, it's also the one that probably results in the majority of failures out there. And you may get an appreciation of that after today because bending stresses really get high because of the bending moments can get really high, especially for particular geometries, okay? So this is what we're talking about in chapter 6, right? So the first thing, what we're going to cover today, which is something you also covered in statics, but that's the construction of the shear and the moment diagrams. So bending has a couple of things that are a little bit different, right? Finding the internal torques and the internal normal forces for axial and torsion problems were actually relatively straightforward. But because the bending and the shear actually change from point to point in general, it's a little more involved. So we're going to go back and revisit how do you figure out the shear in the moment for a beam, okay? We're going to do two approaches, and you are responsible for both of these, okay? So one is to do it analytically. We're going to just write the equations for the free body diagrams. It's a little bit cumbersome, but it's, you know how to do it. And then the second approach is the graphical approach, which maybe you have not seen before. And it requires a couple of little tricks, nothing too complicated, but it does make the construction of these things much, much, much simpler. Okay, so that's why I'm going to kind of require both approaches. Then, like with axial and torsion, we're going to talk about the kinematics, the motion of beam bending, and those assumptions. So classically, these are referred to as Euler-Bernoulli beam theory. Okay, so we'll talk about that, and then we're going to derive the flexure formula. This is going to be like the most important equation. The bending stress, which turns out to be a normal stress, is going to be the bending moment times the distance from this so-called neutral axis over this geometric quantity I, right? So this looks again a lot like, remember from torsion, TC on J. So M is the relevant internal quantity, the internal bending moment that we need. C is the distance to the point in question, much like the radial distance. And we're going to have a different geometric factor, I, which is a lot like J, but it's just in rectangular coordinates, not polar coordinates, okay? So we'll talk about that. We'll talk about calculating I. It gets a little trickier because we have built up sections, and we'll talk about one of these big tricks that we use actually for a lot of things is this parallel axis theorem, okay? But today, we're going to focus on these, okay? All right, because if you can't do that, it's going to be hard to do the rest of the chapter, okay? So this is pretty quick. Although, again, you know, you've seen most of this. All right. So let's talk about what the book has established as the positive sign conventions, okay? So we do need to stick with this because, you know, this is how the solutions in mastering going. And most textbooks do it this way. There are a couple that flip the sign convention for V, but, you know, this is what the text does here. So we're going to call this direction X and this direction Y, okay? And so if we have external loads on the beam, so this is a little beam here, going in the up direction is called positive, all right? Down is negative. Now, when we talk about the shear force, V, in the beam, oops, I'm sorry, what am I doing? Oh, I have to start. Remember, we had been talking about these sign conventions in such a way that we could either cut the beam so that the outward normal is in the positive X direction, that would be like this face, or in the negative direction. So this is the positive face, and this would be the negative face with respect to the X axis. So V actually going down is the positive direction on the positive face, okay? So it's a little bit different, but that's what we use, okay? You can also, like I said, there are some books that flip it, okay? But this book does it that way. I like it the other way, but what I like doesn't matter. I'm going to do what the book does, okay? And then obviously on the negative face, it flips the other way. For the internal bending moment on the positive face, it is what we've always done, which is counterclockwise is positive. And on the negative face, it flips, so it's clockwise being positive, all right? So those are our conventions, okay? Nothing really magic about it. It's just what we have to do, okay? All right. Any questions on that? I think that's pretty straightforward, right? All right. So let's do a simple problem here, okay? So here's problem 6.1. This is actually a homework problem for y'all. And we're going to do this problem twice. So first we're going to do it the analytical approach, and then we will do it with the graphical approach. I hope I can do it all on the slide here. I'll try to be neat. And get it to work out. So here we go. Here is our the component we're talking about. They want us to find or draw the shear and the moment diagrams and figure it out as analytical expressions over the whole length, okay? So the reason they break it up into those three regions is because those are regions where we have jumps because there's point loads applied, okay? All right, so the first thing we need to do here is we need to determine these reaction forces, okay? So I'm going to call this a Y, and this is the Y, all right? So those are the support forces. We'll need those, okay? At least need one of them, all right? So if we were to do sum of moments around A, for example, equal to 0, that is going to give us minus 800 pounds times 3 feet, right? Plus BY times 5 feet is its moment arm, right? And we have the 500 pounds, which again produces a negative moment, a clockwise moment. So it's 500 pounds. Whoops, okay, don't do that. And its moment arm is from A all the way out to this point where it's applied. So that is 6.5 feet. All right, and that equals 0. So we can use that to solve for BY. And if you do that, we get the following. Yeah, we get a positive 1,130 pounds, right? So that's acting up. So this is 1,130 pounds. All right. Now we can also get, do sum of forces in the y direction equal to 0, and that's going to tell us that AY plus BY equals the down force, which is 1,300 pounds. Or we can get from there that AY is 1,300 minus the 130. And that's 170 pounds acting up. It's much smaller, but it's what it is. Oops, why did I say that? I said 170 and I wrote 175. All right, so now we can start looking at doing the shear and bending moment diagrams. So first, I'm going to look at the shear and the bending moment diagram from X between 0 and 3 feet. So in this section here. All right, so this is where it gets a little different. We have to draw this not like at 0 feet or 3 feet, but we want to find V and M as a function of X in that range from X equal to 0, that's point A, up to 3 feet where we have the 800 pound force. So we're going to draw a free body diagram as follows. All right, where here we have 170 pounds acting up, and we're at some distance here, X, right? So that's X. It's not 3 feet, it's not 0 feet, it's X. So that's going to be valid for any point in this range. All right, and then what's going to balance that out? Well, this is a positive phase, so the positive sense of V is down, and the positive sense for the bending moment is as follows. All right, so again, we can do sum of forces in the y direction, and from that you can see that V of X equals 170 pounds. So it's a positive, even though the force is acting down, because that's the positive sense. And then if we do the sum of moments, right? Do this one now. Let's do sum of moments around point A, let's say. Let's do it around A. Well, no, let's do it around X. We'll do it at X. Let's do sum of moments at point X, right? At point X equal to 0, right? That's going to give us, okay, we have the 170 pound force. That's going to give me a clockwise moment. So it's minus 170 pounds. All right. And its moment arm is X feet. All right. Now it's always a little tricky about whether to put the feet in there or not, right? But then if you put in for X as feet, fine. So that's what it is. So I have X. And then we also have, we can't forget the external moment, the internal reaction moment that's applying on the free body diagram, and that's a positive, so that's plus m of X, and that's going to equal 0. So that gives me that m of X equals 170 times X, okay? And that's in pounds, right? So again, this is only between X of from 0 to 3 feet. So if we were to plot this, I'm going to plot V here. So here is V of X, and here I'm going to plot M of X. Obviously, this is X. All right. So V of X, at least between 0 and 3 feet, I'm going to put the points here. All right, is just a constant positive 170 pounds, okay? All right, so that's what it is, right? That's 170 pounds. Now the bending moment is whoops, what happened? Why did it disappear? To there, right? The bending moment starts off 0 at X equal to 0 and goes up at a slope of 170 until we get to 3 feet. So that's going to give me 170 times 3, or 510. So that's going to go up here to 510. Now these, let's just put all these units as pound feet for now, okay? And this slope here is 170, right? Okay, so that's where we are for now. Okay, so now we need to go from 3 feet to 5 feet. So this region here, between the 800 pound force and point B. So I'm going to erase this and then draw the free body diagram for that second segment, because I don't have a lot of space here on the slide, at least. Okay, come on. All right. So now we got to draw a cut through this section, okay? So if I draw that free body diagram, it's going to look like the following. All right. So up here at A, again, we have 170 pounds acting up. Then we go 3 feet and we have 800 pounds acting down. And this distance here is the 3 feet, right? Now this distance here is still X, right? We're at X. And the shear force is acting down, and the moment is counterclockwise. All right. Okay. So this little distance here, right, is going to be x minus 3, correct? Or 3 feet, I should say, right? Right, everything's in terms of x. So this will be valid for any point between where the 800-pound force is applied and point B, all right? Okay, so we can do sum of forces in the y direction, and we get 170 minus 800 minus v equals 0, or in that case, v of x is going to be 170 minus 800, correct? Yeah. Yeah, 170 minus 800, which is going to be minus 630. All right, so that means the shear force is actually acting up. And so it's a minus, so it's constant from this whole section. So it's good. Oops, that doesn't look very constant. Right, so for this region here, it's going to be minus 630. All right, so here we are here. We got a positive shear in this region. And then we jump down here to this negative shear. All right, now we want to get the moment. Okay, so to get the moment, we'll do sum of moments around, again, let's do sum of moments around the cut point. That makes it easier, so I don't have to deal with V, but you know, you could do it in terms of V. So if we do sum of moments around point X equal to 0, that's going to give us, okay, the 170 is still a negative moment, and its moment arm is X. The 800-pound force is going to give me a positive moment, right? 800 pounds. But here is its moment arm, this distance here, which is X minus 3 feet. All right. And then lastly, we have the positive moment M of X. And that all equals 0. So in that particular case, right, we get M of X equal to, all right, so I swing, so I get a constant term here, minus 2,400, but that's going to go to the right-hand side, so it's going to be 2,400. And then
Professor?
Yeah.
I have a question. Wouldn't the moment go downward since it's going, oh no, wait, it's positive, never mind.
Right.
Yeah,
It's a positive moment, right? Yeah.
Yeah.
I think I did it right. Yeah. M and the 800-pound force give me a positive moment. The 170 gives me a negative moment around this point here. Yeah. Okay, so 2,400.
I wanted to ask, like, for the 170, why did you turn it negative again? Like,
well, because around this point here, it's going to produce a moment that goes in the clockwise direction. So that's a negative moment. Right?
oh, okay. Yeah. Oh, because of the reverse thing. Okay. Yeah.
No, not because of the reverse thing. Once we're doing the stuff on the free body diagram, this is the same way we would have done it in any of the previous chapters. Okay.
Oh, okay. All right.
Right, because I wish here's the point X. Here's the 170-pound force. It wants to put a moment going clockwise, and clockwise is always negative, right?
Mm. Yeah.
Right. We don't flip signs like on the free body diagram. We only flip the sign convention. So that means, like, when we draw, okay, V going this way, it's positive, or V going this way, it's positive. Does that make sense?
Yeah.
Once you do sum of forces or sum of moments, it's the same as we've always done it, okay?
Okay. Yeah.
Okay. So M of X equals the 800 times 2200, and then I get minus 170 plus 800X, which is 630 plus 630, so it's minus, did I do this correctly? All right, so X has a, you're putting an X in terms of feet, right? So I think I did that correctly, right? Let me just double check. Right, minus 630. Okay. So, all right. So it's going to have a slope of minus 630. Okay, if we evaluate it at X equal to 2, so at this point here, what do we get? Okay, that's weird. Did I do it the wrong way? $630. Oh, right. I'm sorry. It's at, this is 3 feet. What am I doing? I'm doing it at 2 feet. We want to evaluate it at 3 feet at that point, right? Sorry. I bet you that'll work out now. Right, we get 5, 10. We get the same value, which is what you should get. There should be no reason for the moment to jump. And then it's going to drop with a slope of minus 630. So it's going to be much steeper. And over 2 feet, right? Over 2 feet, it's going to drop 630 times 2, right? And so that means it's going to drop down here to negative, oh, come on, stop. Negative 750. All right. So that's the moment plotted there. All right. So this is all positive. And now we've got a negative moment here. All right. So we're good up to there. All right. And finally, now we're going to go back and do the last section from 5 feet to 6 feet, this little segment here. All right. So let me erase this. It takes forever to erase. So I'm going to draw a different free body diagram. I'm going to draw it from the right-hand side. I'm doing that for 2 reasons. One, because it's a little bit easier. And also so you can see the sign conventions for the negative side, right? Because there I'm going to do a negative side. Okay, so while I'm erasing, could you all type into the chat your name and your email address? Do it in one, please, if you could just do it in one line, full name, like it shows up on Goldmine, and your email address, okay? So why don't you guys do that now? And I'll draw the free body diagram. All right.
Professor, how did
Yes.
you get the 720 again? The 750, sorry.
Oh, okay, because this slope here was, what was it, 630, right? I should have kept it written up there, right?
It was 630.
Right. Okay, and so it's going to start up here at 510, and then it's going to drop down 2 times 630, okay? So this jump between here and here is 2 times 630, right? Or 1260, right? And then you subtract that off of the 511. I think that gives you negative 750, if I did it correctly. I hope. I'll check. I think it is. Just evaluating the expression there. Do you know what I mean, right? I mean, you could put it in the numbers, right? But it's the same difference, right? Yeah. You know, like I'm just evaluating that expression. Whatever, I forget what it was, right? The 2400 minus 630x, right? I'm evaluating that at x equal to 5, right? That's the other way to do it. You'll get the same answer, okay? All right, so here we are, right? So I've drawn the free body diagram from this cut point X through to the right-hand side where the 500-pound force is applied. We could have drawn the other one as well, but this one's a little bit easier. There's less going on. So now this is a negative face that's exposed. So V of X is actually going up, and the moment is going to be clockwise, right? Because everything flips. All right. But now we're still going to do this by, the typical force up is positive, moment clockwise is negative, that sort of thing. So X is going still from the left-hand side to this point. So this is X shown here, right? So this distance here, all right, is not 1.5 feet, but it's the total distance, 6.5 feet, minus X. Does that make sense? So if you're at X equal to 6 feet, right here at the knuckle, you only have 1/2 of a foot of moment arm. If X is right here at point B, if X is 5 feet, then you have 1.5 foot of moment arm to the 500-pound force, or if you're somewhere in between, you're somewhere in between, right? Okay, so in this particular case, we can see that V, we do sum of forces in the Y, V of X is going to equal 500 pounds. So it's a positive shear. So we're going to jump up here up to 500 pounds. It's going to go all the way to the end. And that makes sense because once you get to the very end here, it gets canceled by the 500 pounds acting down, and we go to 0, right? Because it's in equilibrium, okay? So it has to be 500 pounds. It makes sense, right? Okay, then if we do sum of moments around the cut point, if you will, right? We're going to get minus M of X, because it's a negative. And then the 500-pound force is also going to give me, oh wait, what am I doing? Did I draw this the wrong way? I drew this the wrong way. I'm sorry. I said it the right way, but I drew it the wrong way. It has to go this way, right? That's the negative direction. So it's a negative M of X. And then the moment arm from the 500-pound force is also negative. So it's 500 pounds times its moment arm, which is 6.5 minus X. And all that equals 0, okay? So in other words, M of X is gonna equal, minus 500 times 6.5 minus X. Okay, so the slope is going to be a positive number. It's positive 500, okay? And so if you think about it, right? here we were at, well, okay, I can figure it out. So we expect this equation to also calculate to set minus 750 at x equal to 5 feet. Let's just check that. We put 5 feet in for x. We get 1.5 times 500, which is negative 750. So it starts here and then it goes up with a slope of 500. So going up to here, it doesn't quite go to 0. It goes to 6.5. It goes to the minus 250. And the reason it doesn't go to 0 is because this 500-pound force is outboard by a half of a foot. So it's actually, I could have moved that force right onto, this is the same as just considering the shaft out to the 6 feet. With the 170 up here, the minus 800 down. And now if we move the 500-pound out to the 6, that's fine. But we have to add the moment, which is going to be a 250, because we've moved the 500 pounds a half of a foot. So its effective moment is 250. And it does calculate out to minus 250 there as well, all right? If you consider this, if you took this out an extra half a foot, it would go to 0, all right? Okay, so that's how we calculated it, right? We've gotten the equations. This is the analytical method, right? You have to be a little bit careful, but it works, okay? You would have gotten the same answers for this if you used the free body diagram to the left, or likewise, you could have used the free body diagram right to the right for x from 0 to 3 feet or 3 feet to 5 feet. You will always get the same answer, but remember, we have to draw when we use a negative face, we have to draw V and M in that same sign convention, the flip one where it's V is up and M is clockwise, okay? All right? But you always get this, other than an algebra mistake, you'll get the same exact answer, okay? Any questions on that? All right. So, you can do other ones. It gets a little tedious, especially when we start doing distributed loads.
For those, we're going to integrate, correct? Or
yeah, you can integrate those, but we'll do the graphical method, which basically is integration, but you can do it by just finding the area under the curves. But a couple of things that you can note here is, when you have a point force applied, right, you can see that the shear diagram actually jumps by that exact point force. So initially we have the 170 pounds acting up. So we jump up to a positive 170. Now, when we hit the 800-pound force, we're up here at 170 and we drop down 180, right? I'm sorry, 800. I'm sorry, not 180, 800. That's so hard writing on this thing. 800, right? And that gets us to the minus 630. And then between here and the 500, how much do you think that jump is going to be? This jump here is going to be exactly the same as the point force applied at B. That's the jump at B. So it better be 1130. So let's just check. So if we had 500 to 630, yeah, it's 1130. So that checks out. So the shear diagram is going to jump depending upon what the point forces are, right? And then when we get to the very end, there's a 500-pound force, so it jumps back down, right? Likewise, with the bending moment diagram, it's the same thing. There is no external moment at A, so we start off right at 0, okay? There are no point moments applied anywhere, So everything is continuous until we get to the very end here at x equal to 6 feet. And we didn't quite hit 0, but that's because there is an external applied moment of 250 pound-feet due to the fact that we moved the 500-pound force statically out to that point, that 6 foot mark, okay? All right. Okay, so we have to do a couple little equations here first, just to do this graphical approach. But here we have a beam, okay, with some generic distributed load applied onto it. And now we're gonna look at a differential segment here, all right? So the external load is given by W of X. So obviously that's gonna have units of force per length. It's a distributed load. All right, so if we take a little differential element to the beam and blow it out here, we get the following, right? So on the positive face, we have the shear force acting down and the moment acting in a counterclockwise manner. On the negative face, we have it flipped. The shear force is up and the moment is clockwise. So this here is X. So right, that is at point X. And then out here, we're at X plus delta X, right? All right, so on this face at X, the moments are simply M and V. Now, if we move out a little bit to here, we move out by delta X to the point X plus delta X, you know, the shear and the moment will change a little bit. And so there they are. They're given a change of delta V and delta M over that differential segment delta X. And what else is going on here? Right? We have the distributed load, which what they've done here, right, is simplified it and just assume, because we're going to let delta X go to 0. So it just takes W times delta X. It takes that as the value, but really that's, you know, there's actually a curve, okay? But we're gonna take delta X to 0, so that's what it is. All right, so let's look at this, right? If we do sum of forces in the y direction, what do we get? V plus W times delta X minus V minus delta V equals 0, right? And so the V's cancel out. And here I can just rearrange this. I can get delta V equals W times delta X, or dV dx equals W of X. All right, as we take the limit as delta X goes to 0. So this is telling me that the slope of the shear curve equals the value of the distributed load at that point, okay? All right. Also, you could have integrated that and you could get that delta V is equal to the integral of W of X times dx. So that means from one point to another, the shear will change by the integral of that distributed curve or the area under that curve, okay? So these are the same relationships. All right, so let's look at sum of moments, okay? So if we do sum of moments around O, all right, if I do that, I'm gonna get, let's do it on this face. So I get minus M, that's a negative moment, minus V times delta X, because this force V has a moment arm of delta X around point O. Here's point O. And then the distributed force is also going to give me a negative moment, minus W delta X. That's the value of the force. And its moment arm is is 1/2 delta X. All right. And then the shear force V plus delta V doesn't do anything at O, but we have the positive moment of M plus delta M. And all that is going to equal 0. So again, the M's cancel out, all right? And we can rearrange this, and I can get delta M over delta X. You probably can imagine where this is going. That's going to equal V, just V because I divided by delta X, plus W delta X over 2. It was delta X squared, but I divided by delta X, okay? And then if we take the limit as delta X goes to 0, we get dm dx equals, well, V is just V of X. And this term here is going to go to 0 because delta X goes to 0, right? So here we get something that looks very similar, right? And we can also write this in its integral form. Delta M equals the integral of V of X. All right, so what does this mean? Well, this means if I have a shear diagram, if I know the shear, the value of the shear at the point X has to equal the slope of the moment curve. Or likewise, if I wanted to figure out from how much the moment changes from one point to another, all I have to do is integrate the shear curve between those 2 points, okay? So this is graphical because we're not gonna really do the integrals formally or the derivatives formally. We're just gonna recognize that the derivative is the slope and the integral is the area under the curve, okay? So let's look at this. So here's an example the book does, pretty good, right? Here's a distributed curve. It has some shape. It's not quite constant or linear. Maybe it's a quadratic. Maybe it's a hyperbolic sign. I don't know, okay? But this is the curve W of X. So if we want to construct the shear diagram, right? Well, the first thing we're going to do, before I go up, the first thing we're going to do, right, is figure out the sum of forces in the Y and the sum of moments. And this is going to give me the shear force here, the reaction force here, A of Y, and then the reaction force here of B of Y. So we can calculate that from, the equations of static equilibrium, right? And here we can graphically construct the shear curve, right? So at X equal to 0, right? We know if you were to just consider a cut just ever so slightly over from point A, here you would have AY acting up. The positive sense for the shear is down. I'm going to let this distance here go to 0, like in the limit, but clearly here you can see V of X has to equal AY at X equal to 0, right? And so we're going to start off here at AY. All right. Also, we know that the distributed force here is 0. At this point, W of X equals 0. So from here, we know that the slope of the shear curve has to also be 0. All right. Now, the shear force, the external force here is down. So this is negative, right? It's negative. That's in the negative direction. So again, right, at each one of these points, you could figure out the slope of the shear curve by figuring out what is the value here and here. So the slope of the curve at this point is going to equal the distributed force evaluated at point C, and the slope here is going to be the distributed force at point D. Well, and that's going to keep going negative, and it's going to keep increasing because W of X keeps increasing until we get to point B. All right. Now at point B, all right, we have BY, and it's going to jump up by the same amount to BY. So this value here is going to be minus BY. I don't know all the details about like what all the numbers are between here and here. And I don't know exactly where this goes to 0, but I've got at least the general shape of this of the shear moment, the shear diagram, and I know the values at the ends. So you can do that relatively quickly, right? All right. I mean, I don't know what they are, but let's say this is 300 pounds and this is 500 pounds, right? So that means the shear diagram is going to start off here at 300 with a slope of 0 and then kick down to a slope down to here where it's going to be minus 500, right? And you can draw the approximate shape here, right? So you really don't need any equations. Okay, so now that we have a shear diagram, we can get the moment, all right? So, fine. So, again, we know that there's no external moment here at point A, so the moment curve is going to start off at 0. All right, it's going to have a slope equal to the value of the shear curve. We know the value of the shear curve here is that support force, so we start there. And since the value of V keeps decreasing, this slope is going to decrease. So it's concave down, right? Until eventually it's going to get to a point where the shear curve goes to 0, and right there, you're going to get the moment equal to 0. And then we know that there's no external moment at B, so it has to go down to 0 here, and it's so we could draw it kicking down, and actually we can even get the slopes because that's going to equal VB. All right. So the only question here is, what is this value? Like, we would want to know that, right? Because that's the max, right? How do we get that, right? Or how do we know where this goes to 0, right? Well, there we can use the integral relationships. So we don't know what this value is, right? But remember, from this, we can also write that the moment, or the change in the moment, is equal to the integral of V of X dx, right? So that means this value here is equal to, or I should say the change from here to here in the moment curve is equal to the area under the shear curve, right? So this value here is going to equal that area, all right? We're going to use this integral form of this relationship to tell us what the value is of the moment. You know, you could use the same thing here to figure out where it goes to 0. So we want to find out the point where the integral under this curve equals the value of AY. That's going to be the point where it goes to 0. Okay? So that's what we mean by this graphical approach, right? All right. Oh, whatever, this is the same stuff. Oh yeah, and I should say, like, oh, this is what I'm gonna do. So like if we had a point force again, right? Let's say we have a point force, and then we can do a point force. Let's say we have something like this. All right. And let's say this is 200 pounds, and this is 300. Let's say this is 500 pounds, and this is 300 pounds, right? All right. So if we were to construct the shear diagram, right, Okay, just a little bit past here, the shear force to balance that up 200 pound is going to be down. So that's a positive shear. So we're going to start off here at 200. All right, fine. So what happens here at this point? Well, there is no distributed load to integrate on, right? But this is a point force. It's like what some people call a Dirac function, right? And if you integrate that, you get the actual value, right? So it jumps down that 500 to minus 300, and then it kicks back up here. So when we hit a point force, like as I described before, actually the integral form is what gives you the fact that it jumps by the amount of that point force. This is 500 pounds, all right? So with using those things, area under the curve, the slope relationships, also trying to figure out where these zero crossing points are, this allows us to actually sketch these things out with a good degree of accuracy, you know, without having to resort to all those equations, okay? So let's do this again for the same problem we just did, all right? So you still have to do, you know, calculate the support forces. So we knew that we did this already. So this is 170 pounds. And up here, right, we have the 1,130 pounds, right? We already figured that out from sum of forces and sum of moments on the total diagram. So let's just construct the shear diagram from here, right? So let's do it here. Right? So here we're going to construct V of X, and this is X, and let's see if we can draw this reasonably well. So here is at 3 feet, and then here is 5 feet, and then finally at 6 feet, right out to this point. Okay. All right. So again, if we look at the, you know, a free body diagram just a little bit, you know, in the limit as it goes right to point A, we can see that the shear diagram has to start off at a positive 170. All right. Now between A and 3 feet, W of X is equal to 0. All right. So the slope, right, dV dx is also equal to 0 because it's equal to W of X. So we're going to just go straight line over to here, which is what we got before, right? All right, now we hit 800. So, you know, once we integrate past the 800, that means it drops down by that 800. So we're going to go from 170 down by 800. So that is 6 to minus 630, right? From the jump relationship, right? And again, between here and here, W of X is 0, so the slope is 0. We go to here at 5, and now it's going to jump up by the 1130, and probably off the charts here, but whatever. So 630 or minus 630 plus 1130, that's going to get me up to 500. And then that drops back down to 500 because we have the 500 external applied there. All right. Now, you know, how do we know which, you know, is this a positive jump or a negative jump? That sometimes can be a little confusing. But the way I always think of it again is like, let's just look at it just barely over from where we put, here's the 1130. Right? So we're going to let this distance here, dx, go to 0. So this is a positive phase. So the positive value of v is going down. So if you do sum of forces here, this has to equal the 1130. So it's a positive jump, right? If v were going the other direction, then it would be a negative jump, okay? And I guess you could remember that too, but I always forget those things. So I just kind of draw the little free body diagram to show me whether it's positive or negative, okay? All right, so there you go. That's the same shear diagram we got before. So now we got the shear diagram. Let's figure out the moment diagram, all right? So here we're going to draw the moment diagram, m of x, and it's going to have units of pound feet. All right. So again, we're out here at 3 feet, 5 feet, and then 6 feet. Okay. All right. So same argument. At A, there is no external moment. So if you were to look at the moment, internal moment, right at like a little free body diagram, just barely over, right? You would have 170 up. And then we know we have the V equal to 170 going down, right? And then we got this moment, right? But if we let this delta x go to 0, the moment arm is 0, so that means that the moment has to actually go to 0 as well. Basically, if there's not an external applied moment there, the moment curve is going to start at 0. Likewise, if we do the static equivalence here, and we just bring it out to 6 feet, right? We have 170 acting up here, the 800 acting down, the 1,130 acting up, and then right here at 6 feet, if we move this force into the 6 foot point. Wait, what? What's going on? I don't want to do that. Why is it exiting out? Keep. What are you doing? Just delete everything? Jesus. I hope not. Where are we? Okay, where are we? Back. All right, here we are. Okay, let's go back to slideshow mode. I don't know why I jumped. All right, so what was I saying? Yeah, so we're back here. We got 500 feet, 500 pounds acting down, but since we moved it a half a foot, right? That means that we need to apply the moment here of 250 pound-feet, right? All right, so that means that that's actually a moment that's applied, that's an external moment. So if you look at, again, just a little bit over from there, right, here's the 250. Oh, why was it written 250? It's fine. All right, since that's 250 times 500, then this is a negative phase, so the positive sense is going to be clockwise. So this is m of x. So here you can see that m of x has to equal negative 250. And again, we don't have to worry about all the other stuff because we're going to let this distance here go to 0, okay? So m of x is minus 250, so we know right here we have to be at minus 250. All right. And then fine. So, right. So the slope, so the slope of the shear curve is equal to the value, I'm sorry, the slope of the moment curve is equal to the shear curve, right? So the value here is 170. So that means the slope is going to be constant and positive 170. All right. The value here, right, has to be the area under this curve, because we know that the change in the moment is equal to the integral of v dx. So this area here is 170 times 3. So that area is 170 times 3. So that's 510. Sounds familiar. Its units are going to be pound feet, because it's 3 feet times 170. And that should also be this, right? If you think about it, right? That's 170 times 3 is also 510. So we go up here to 510. Okay. Now we're going to have a negative slope of 630. All right. And it's going to jump down by this amount here. So this amount here is 630, or I guess it's say minus 630 times 2 feet, or that is negative 1260, right? So 510 minus 1260 gives me the minus 750, which is what we had before. All right. And even if we wanted to, we could figure out where this zero crossing point is. All right. Not that it really matters, but you could figure that out just by the, the geometry here, or starting at 550. Like if you go at a slope of negative 630, how far till you drop by 510? So this distance here, right, would be 630 over, wait, I'm sorry, it would be 510 over 630. Right? So that would give you that distance, right? Okay, and now we're going to go back up with a positive slope of 500. And that's going to come back to here. And you can check that, because this distance here, the amount that the moment curve changes, has to equal this area under the shear curve. So that is, this area here is 500 times 1, or just 500 pound-feet. And if you go from 750 up by 500, that brings you to the minus 250. So it all works out. Okay. So I know it's a little trickier doing it this way, because you have to kind of keep a lot of things in your head. You have to remember, those equations. I suggest maybe writing them on a piece of paper, or even more importantly, internalizing them as a concept, that the slope of whenever we start off with W, and then we go to V, and then we construct M from V. So we have the distributed load curve, we construct V from that. So the slope of V equals the value of M, or the change of V equals the area under the the distributed load curve. Then when we go from V to M, right, from here to here, it's the same stuff, except instead of the distributed load, we have V, the shear, and instead of V, we have M, okay? Look for the 0 points, that sort of stuff. So, there's more things to or more concepts to kind of struggle with a little bit. But if you get used to doing it, you'll find it'll take like almost no time to construct these shear and moment curves, okay? All right. Is there any questions on that? Okay. Basically, the next thing that we would cover is the flexure formula stuff, but I am, I only have like 10 minutes, so I think we'll stop here. That was basically what I wanted to go over today anyway, so. I don't know, any questions on this material or on anything else? You know, we already did have a review class for the exam and it's on the same material, but I will try to set up maybe on Monday evening something if, you know, just so people can ask last minute questions. But even if you do have questions, remember you can always post those in the discussion board on Blackboard, okay? And hopefully I start to receive emails sometimes, okay? All right. Well, if there's nothing else, then,
Professor,
yeah,
we will be able to email you during spring break, correct? Or no?
you should be able to.
Okay.
For some reason, my accounts are being particularly problematic for them to set up. The help desk is looking at it. You should be able to, okay?
And then we email you to the Gmail still, correct?
You can always do the Gmail one. I'll still keep checking that one, right? But
Okay.
I'm hoping to get my UTEP one fixed like in the next day or so anyway. So. But yeah, if you want to make sure, you can always do the Gmail one, okay? Because I'll still
All right.
check.
Then. Thank you.
All right. Okay. Any other questions? All right. Well, if not, I think we'll call it a day then. All right. Have a good spring break and stay safe, okay?
Thank you, Professor.
Thank you.
Take care.